Okay, so the last two reactions we're going to cover are not electrophilic aromatic substitution reactions. Instead, they're different types of aromatic substitution reactions. The first one we're going to look at is called nucleophilic aromatic substitution. And so let me show you an example of this first, and then what we'll do is we'll dive into the mechanism. In this example, what you have is some sort of leaving group, and you have some sort of strong electron withdrawing group. So these are the key features, is you must have a leaving group like this bromine, and you must have a strong electron withdrawing group. And that electron withdrawing group needs to be ortho or para to your leaving group. All right. And in this reaction, what we're going to do is we're going to treat this with a really strong nucleophile. In this case, even hydroxide is strong enough to work. So I'm going to label this as a strong nucleophile. Has to be something with a negative charge. And then in step 2, we're going to quench the reaction with dilute acid. And when we do this, what's going to occur is a substitution reaction where the bromine is replaced with an alcohol, and then the nitro group stays put. A lot of students are tempted to presume that this is an SN2 reaction, like we saw in first term, but the mechanism is entirely different. So let's take a look at the mechanism for how this works. All right, so the mechanism, let's first redraw our starting material. We've got our bromine. In this case, it's para to our strong electron withdrawing nitro group. And we've got hydroxide as our reagent in step 1. All right. And when we think about this reaction, we know that a nitro group is a really, really strong electron withdrawing group. And if we were to draw the resonance structures, we would see that there's a partial positive, para, and ortho to that nitro group. If anything, that reiterates why in electrophilic aromatic substitution reactions, the meta positions are the most reactive. It's that the para and ortho positions are not nucleophilic. All right, so we've got this hydroxide, and the hydroxide is going to attack one of those electron withdrawn positions. So let me clean up my arrow. It's going to attack right there, and it's not going to kick off the bromine. We know that it's not going to do SN2, so we must do something else to prevent violating the octet rule. The most rational thing to do is to actually kick electrons from the pi bond over to one of the adjacent carbons. Okay, so we're almost there. We've got this nitro group. We've got our alcohol. We've got our bromine. And we've got a negative charge right there. The reason that this is favorable is this negative charge can be delocalized via resonance. In particular, I'm going to show this nitro group with all of its bonds. In particular, we've got this nitro group that's very strongly electron withdrawing. So it can take this negative charge. Let me keep my arrow colors consistent. And it can actually delocalize that negative charge all the way over to one of the oxygens in the nitro group. That gives each oxygen a negative charge and creates a relatively stable, resonance stabilized intermediate. All right, so I'm just going to slide everything over. There's more resonance structures you can draw, but this is going to be one of the major contributors because we can get that negative charge to end up on an electronegative oxygen. This whole thing is called the Meisenheimer complex. It's not a sigma complex. A sigma complex has a positive charge within that aromatic ring system. In this case, it's a negative charge, so it's quite different. All right, in the next step, what we want to do is we want to eject off the bromine. So I'm going to go ahead and just clamp everything down through a cascading fashion and kick off that bromine. So we're almost there. We've kicked this all off. We've reformed our regular nitrogen group, so I'm just going to show it like that. However, this reaction is almost always done with excess hydroxide. We have to push the reaction to completion, so oftentimes there's excess reagent used. So it's going to grab this relatively acidic proton right here and give us the alkoxide, specifically the phenoxide. This is relatively stable because this negative charge that we're creating is resonance stabilized. That's why that proton is so acidic. So that's why in step 2, we must treat this with some sort of dilute acid in order to reprotonate our product. So this is going to be step 2. Going to grab this proton and we'll reform our desired product. All right, so let's just make a list of the key requirements. Number 1 is you must have a leaving group. So typically things like halides or tosylates work well. Number 2 is your leaving group must be ortho or para to a strong electron withdrawing group. And in fact, it can be more than one electron withdrawing group. In fact, that's more favorable. So we could have had even some more nitro groups on this ring that would have driven this reaction to occur faster. So these are the key requirements anytime you're doing a nucleophilic aromatic substitution reaction. All right, so that's one reaction. Let's take a look at the next one. The next one that we're going to look at is called Elimination Addition. And Elimination Addition is kind of different than all of these, but it's a little confusing. So let's take a look at some various situations. So let's say we don't have a strong electron withdrawing group, and we try to run this reaction with hydroxide during step 1, and then acid in step 2. Typically you get no reaction at reasonable temps. So you don't get any sort of substitution reaction to occur. All right, what you can do is you can just heat the snot out of it, get it really, 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 really hot. So I'm going to even do that in red to emphasize it has to be super hot. And if you get that to occur, you can actually push a reaction where you can replace that bromine with an alcohol group. However, this requires really high temp. High enough that it oftentimes will degrade your starting material, so it only really works well with simple aromatic molecules. All right, but there's one interesting thing that was observed while they were studying this reaction, and that was if you have a stronger nucleophile and base, something like NH2-, you can actually do this reaction quite readily. Whoop. Let me even change this to NaNH2 so we can account for our counter cation. And this is typically run in liquid ammonia. And when you do this, this will actually work at moderate temperatures. So a lot of scientists argued about this, and they said, well, isn't that due to the NH2 potentially being a better nucleophile? Not quite clear, right? Because when we think about nucleophile strength, yeah, it's going to be a stronger nucleophile, but maybe there's something else going on because it's also a really, really good base. So there was some debate as to the mechanism for this. It wasn't until this landmark study came out that a mechanism was proposed. So let's take a look at the mechanism for this. And the mechanism is kind of interesting. If you have a halogen, and let's just say some unreactive group, CH3 group, and you treat this with your sodium amide, which is NH2 minus, that's your active reagent, it's not going to attack the carbon with the bromine. Instead, what's found is that it will do acid-base chemistry. It'll grab one of the protons adjacent, and it will do something that almost looks like an E2 reaction. So when you do this, you end up making a triple bond in this aromatic ring. So this triple bond is kind of unique. This molecule is called benzene. It's highly, highly, highly unstable, but that's okay. If you have more sodium amide, it can act as a nucleophile now and react with this really unstable intermediate, and it can kick electrons back over. That gives you a negative charge right there. And then in the last step, we just need a really weak source of acid, which is going to be ammonia in this case. And this will rip a proton off of ammonia in order to get to the neutral product. So here's the interesting thing here, right? The amide, this NH2, acts as a base in step 1 to do an elimination reaction. But then it does an addition reaction in step 2, where it acts essentially as a nucleophile. So it's acting in both capacities. However, the interesting thing from the study was there's actually a second product that's also observed that supports this mechanism. And this second product is where this negative charge can attack the other side of the benzene and kick electrons to the top carbon. And if that happens, the NH2 is going to be installed off of a different position. And you'll actually get 2 different constitutional isomers as your product. This mixture of products is actually what was used to elucidate the reaction mechanism, and we know that it's not going to be nucleophilic aromatic substitution, because with nucleophilic aromatic substitution, you would only get this top product, you wouldn't get any of this lower product. So this is the only mechanism we were able to come up with that accounts for the formation of both of these potential products. So kind of a cool tidbit of chemical history. All right, so really quickly, let's just look at the chapter summary. This chapter, we covered a lot of reactions, and we saw that we can do a variety of electrophilic aromatic substitution reactions. You should know the mechanisms and reagents required for each. And then from there, we can form derivatives where we can do things like the Clemmensen reduction, we can oxidize benzylic carbons, we can do bromination of benzylic carbons, we can reduce nitro compounds, all of that good stuff. We also just covered these last 2 reactions that aren't electrophilic aromatic substitution reactions. The first one was this nucleophilic aromatic substitution, and then the second one was elimination addition. Down here we've got a really good flowchart for how to decide what reaction pathway is occurring. And the first thing you do is look at whether or not your reagents are nucleophilic or electrophilic, and from that you can determine what sort of reaction pathway will occur. And then last but not least, we talked about activators and deactivators, and we said that all activators are orthoparadirectors, and the deactivators, for the most part, are going to be metadirectors with the exception of halogens. Halogens are always going to be orthoparadirectors. All right, so as you work through your skill builders, feel free to shoot me an email or set up a one-on-one meeting with me, and we can go over any problems or questions that you have. All right, good luck studying.